Now, so then today I'm going to give a assessment of what can be done. I've touched on that somewhat in the past, but today will be a sort of a more complete or coverage of it, of the question. Now, can you all see my slides? If at some point, okay, good. Now, so this, what I want to do is point out a strategy for advancing computational methods in economics. Now, the one thing I like to emphasize is that computation has been not only a part of economics for a long time, but in the past, the computational community and the economics community had many interactions. Ken Arrow, for example, if you look at early papers on the theory of constrained optimization, you'll find papers by Ken Arrow, along with some math guys. And I think there's some other economists involved in that, but Ken Arrow certainly was a major figure in that time. Ragnar Frisch, who, by the way, founded the Econometric Society and Econometrica. Now, in the early 1950s, he proposed a way of solving linear programming, which at the time was not possible to implement because of the hardware limitations of hardware and software. But in the 80s, his ideas became a part of what we call interior point. The other thing that I like to point out is that the SQP method, sequential quadratic programming method, that is a part of so much of the leading software, was first invented by Bob Wilson in his 1964 PhD thesis. Also, the SCARF algorithm, which I think in the mid-60s is he proposed it and published it, was also a predecessor of homotopy methods. So has been, in the past, there was this interaction with the computational community. Now, that interaction has largely ended, or it's very much smaller, partly because what happened in the 70s is every little group of people had decided to have their own little department. And so the interaction really limited multidisciplinary, that structure limited the interdisciplinary interactions. Now, econometrics has been a big user of computation. Much of the methods that they use have been imported from statistics and computational methods. The Monte Carlo method, the basic paper of Click and Van Dyke basically introduced economists to a Monte Carlo integration. Now, more recently, MCMC, Monte Carlo Markov chain, or the other way, I don't know, came from physics. Then the citation that's often used, made is to Metropolis Hastings algorithm. And by the way, that's two papers, one by a guy named Hastings and the other by a paper of 5 authors, the first name being Metropolis, and the other 4 being Rosenbluth, Teller, and Teller. So this is also obviously had a very much of a physics background. Also, nested fixed point method is a low memory implicit optimization method. So used much in econometrics. Now, in policy analysis, computation has been very important, going back to 1960. There's this Norwegian economist, Leif Johansen, who basically wrote the first serious paper on computational general equilibrium. And in fact, his thesis became a book that was published in 1960. But now then, today it's used greatly. CGE analysis is used a lot in tax policy analysis, certainly in trade policy. Very large community there that apply CGE computational general equilibrium models to trade policy, also somewhat so in antitrust. So that's the past. And it's clear that there has been in the past progress in economics using computational methods and some interaction with the computational community. Now, I'm going to cover a variety of aspects of computational methodology in economics and go through sort of where we are today and where we can go. And by can go, I'm staying away from crazy sort of very excessively ambitious things, but point to things that I have done or people I know have done or things that I know are out there just for the taking. So basically what I'm going to cover now is I'm going to cover in particular some topics that I would have loved to do had this been a 2-semester course. So much of this that I'm going to be talking about is stuff that's the next, just beyond what was covered in this course. Now, hardware. Now, economics generally limits itself to desktop computers or small clusters. Things with, less than 100 cores, basically. Now, there's a lot of computing power that's available to economists at no cost. Now, I've described to you the NIAS web server and network-enabled optimization software, where basically you describe your optimization problem, send it to NIAS, and they'll solve it for you for free. You better keep the problem running under 4 hours, but if you have a big problem that takes long, you just break it up into 4-hour pieces, so big deal. And in fact, Carlos Rangel, a student of mine, actually has developed software that can send unlimited numbers of jobs to it. So now, why don't more people use it? Well, the thing is that you have to use particular software that is not commonly used is not familiar to most people in economics, namely AMPL and GAMS, but it's there. It's hardware power that you can get to today. You can just, after my lecture, you can just send them a program and they'll do it. Now, something that requires a little more effort, but not money, is a brand of grid computing called HT Condor. HT Condor, it's software which brings together many computers and then will distribute your work across that that grid of computers. So it is software, but the key thing here is to point out that this is a doorway to a lot of computing power. It is what Young Yang and I first used in our parallel dynamic programming. Now, the reason that we used it is I was able to learn about HT Condor and connect with the leading people of that software, and and then now I'm reestablishing contacts with those people, and also have a couple of students working with me to basically help to teach economists. First of all, we're going to use it for our own purposes, but then also basically help to write sort of a roadmap for how you can use HT Condor, which also then is a doorway to something called Open Science Grid. Enormous amounts of computing power available there at no monetary cost. Now, National Science Foundation funded supercomputers. Young Yang and I got on Blue Waters, and I think we got, one time I tried to add up, I think it was like 30 or 40 million core hours over the past several years that we were able to get. Now, there we found an interesting and not well advertised back door. But we found it. We were told, a friend of mine told me about it, and we used it, and to great success. Now Blue Waters has been unplugged because it's considered obsolete. The NSF now is funding something called Stampede, which of course is at the University of Texas. Now there's another program called XSEED, XSEDE. I don't know what the letters stand for. Just type in XSEDE and you'll go to the website. This is basically another kind of network enabling software where you can get time on a variety of different supercomputers. And there you can get 30,000 processor hours just for putting several sentences together coherently to describe your research. And remember, we're talking about a computer science kind of project, so the demand for coherence and on the proposal side is pretty low. Just basically describe what your problem is, and you can, just for the asking, get a substantial amount of computing time. And then once you demonstrate that you can use it, you can then apply for more time. So that's all American stuff. Now, by the way, it's officially American stuff. But if you happen to know some American and are on good terms with him, he can bring you in. It's again another one of these back doors that you can use if you aren't directly qualified for it. In Europe, some of Carl's students and colleagues have used PISDAINT, which is a Swiss supercomputer. It is the most powerful supercomputer in Europe. And one of the main guys there is Olaf Schenk, and I've seen him. He's spoken at some of our workshops, and he's very supportive of developing computational economics as a branch of computational science. And you see, this is important. It's okay, the supercomputer is there, but if you don't have connections with some people that know your agenda and are willing to support it, well, then it's not worth anything. At PISDAINT, Olaf Schenk has been very supportive. That's been very helpful. Now, I don't know the European supercomputer systems in general, but there again, you Germans, you know what's there, or perhaps my talking about this gives you ideas of how to approach or find things, finding the support that you want. Now, the problem is that, yes, it's free in money terms. It does take some time. You've got to learn the bureaucracy of getting the time. And then with Blue Waters, once we got this amount of time, they said, oh, you have to come to our annual symposium. You must appear. Well, that wasn't so bad because we went, that was held basically a few hours north of here, a few hours by plane north of here in Oregon at a resort, outdoor resort, which is fine, it's a paid vacation. It was very nice. So they had, that's a kind of also the other thing, but it's good to meet other people that are working on the same hardware. Now, economists have generally stayed with popular software platforms, as I've commented on before. Some economists, particularly in the field of applied general equilibrium, use better software and platforms, GAMS, AMPLE, and that gives them access to the most powerful optimization procedures, solvers, and also comes with very powerful features, automatic differentiation and automatic sparseness detection. Now, by the way, this was an approach that Bill Nordhaus used in his first models of dice in the early 90s. So that tells you just something about how old these platforms are, GAMS and AMPLE in particular. And so he used it to great effect, and a variety of other people in the integrated assessment model are using this platform. Unfortunately, recently, Nordhaus has moved to Excel, but I don't think that I don't know why, but Most others are staying with GAMS and AMPL modeling languages. Now, there has been improvement, by the way, to the standard tools such as MATLAB with ADDIMAT and Casati. Now, we've talked to you about Casati. There's also, and I think you probably heard some talking about ADDIMAT. Now, these are powerful tools that extends improves the efficiency and adaptability of MATLAB code. So some of those features of GAMS and AMPL are now available if you use ADDIMAT or Casati and MATLAB code. So there's been progress on that. But the thing is that this is all still basically desktop kinds of stuff. For example, MATLAB is not on supercomputers, and I asked the grandfather of MATLAB, and he said, well, he doesn't like putting it on supercomputers because it's meant to be an interactive software. I don't think Excel will ever be on supercomputers, and I suspect that's the case for these other things. So to get to the higher power computing, you have to, like I said, learn Unix and learn some of these other approaches, but that again is not that difficult. Now, you might ask, well, what are some of the things that in economics where we have computational problems and we have algorithms to solve it that can really exploit serious computational tools? Now, I've mentioned some of them, but then I'll talk about some others. Now, I've talked about the Judd Mallier approaches to solving dynamic stochastic general equilibrium models. Now, those models tend to be with multiple agents, but just one good. But there's a piece in, but it's all the Judd Mallier methods has a modular structure. And so then what you can do is expand the set of goods and then just plug in a standard general equilibrium solver to solve what we could think of as a temporary equilibrium at any point in time. So, but then of course that's going to increase the demand for computational power. But those methods are all very parallelizable. And so we have the algorithm tools to do it. And then once you move to higher power computing, you have the power to do it. I mentioned how NLCEQ can solve complex dynamic GE problems. Now, more recently, Simon Scheidegger and Johannes Brum had a paper in Econometrica where they showed how you could use sparse grids to solve DSGE models of, I forget what dimensionality they had, it was like 100 or 200 dimensions. And that was using sparse grids. Now, by the way, for specificity's sake, this is sparse grids, but not the Smolyak stuff. This is a separate technology that I did not mention at all in class, but Scheidegger is an expert on using it. I actually heard first about sparse grids from a guy who essentially became my student, Thomas Mertens. And this was back in 2005. This tells you how long some of these things take. And he attended the first session of ICE. And we had a poster session and he presented a fantastic poster. I think it's still the best poster ever presented at any ICE session. And he used sparse grid methods to solve a four-dimensional partial differential equation that related to his option pricing. And and then by knowing him, I actually was invited to spend a week at Bonn as a guest of Michael Griebel, who is the sort of the godfather of sparse grids. And now I was hoping to use that and have Thomas help me use that technology. But the problem was that a lot of the software was a bit fragile. Graduate students would write some software to do something and They'd make sure that it was good enough for their PhD thesis, but things like that are often fragile. Scheidegger has written some solid sparse grid software, which now makes it much more easy to use and directly useful and more robust. Now, in dynamic games, Shaveen, Young-Yang, and I had a paper in OR a couple of years ago where we computed all Nash equilibria for some games with states. Now, it's very computationally intensive. It needs massive computing power in order to be used, but that's an example of an algorithm which we now have developed and is available to be used in economics problems if you have enough computing power. And this was done on blue waters, but it also could easily exploit the power in grid computing. And next is writing up software with find all markup perfect equilibria. Now, I'm next going to tell you about a story that basically spanned 15 years. Actually longer if I include the time I've been thinking about it. Most Murley's income tax type problems assume that people differ only on one dimension. And often they differ only in terms of their productivity. And so then Murley's problem is to find optimal income taxation where all you observe is somebody's income, but the only difference among people is their productivity, which a government cannot directly observe. Now, so I've been thinking about that for many years. And then about 2005 or so, Chaylin Su and I started writing up some code to look at problems that had more than one dimension of heterogeneity. People differed not only in terms of productivity, but they could differ in terms of their tastes, maybe elasticity of labor supply, or curvature of the utility function, or different age, or all 3 or 4 of them. And so this is multi-dimensional heterogeneity. When we tried to solve it on standard solvers, SNOpt, CONOpt, IPOpt, whatever, they failed except for small problems. And that was because these problems do not have solutions that obey LICQ. And the solvers assume that the LICQ constraint qualification holds, and our problem didn't. In fact, our problem belongs to a category of degenerate optimization problems. So we had a degenerate optimization problem. I love that term. So I do degenerate optimization problems. Now, so Chaylin and I basically hit a wall on that. He had other things to work on. And so he focused his time on that, and this was all set aside. And then in 2016, Ding Ma and Michael Saunders saw me present this, what Chaylin and I had done up to that point. And I made the point that, well, all of the standard solvers fail. Now, Michael Saunders was in the audience, and he wrote some of those solvers, NP-Sol, SNOpt. So, and I said, well, basically said publicly that Michael's software could not solve our problem. Well, the nice thing about mathematicians is they take this as a challenge and very, in a very good way. So Michael at my presentation said, well, I think you can deal with this by this kind of regularization. I said, fine, let's talk about it. So we did talk about it. Turns out that the ideas he initially had didn't work, which didn't surprise me at all. And so then I thought we had given up. We had about 6 months of conversations, and then I didn't hear from them for 6 months. And then voila, November 2017, I'm sent a paper where I am the second author. Author order is alphabetic, Ma, Judd, Orban, Saunders. And this paper has an algorithm, NCL algorithm, that can solve optimal income tax problems with multidimensional heterogeneity. And the best example in that paper was people differ in 5 dimensions. You end up with over 500,000 incentive compatibility constraints. So here's a problem. You have an objective function, and I think you only have about, I don't know, a couple thousand choice variables, but you have 500,000 constraints. But this algorithm can handle it, even though LICQ fails. And in fact, it's solved in 4 hours. And also, the paper contains the code that was used to solve the examples. And that was all written up in AMPL. So that is, now there's a technology for solving degenerate optimization problems. And that is a phrase that covers not just Murley's style income tax, because actually this is just a kind of principal agent problem. So there's numerous principal agent problems that can now be solved that was prior to this intractable. There's no theory behind them, and none of the solvers could use them, but now this is available. Now on the principal agent dimension, recently Philip Renner and Carl Schmetters used polynomial optimization methods to solve general principal agent problems. Principal agent problems generally have these side assumptions, some stochastic dominance of some random variable, and these are not innocent assumptions. These are special assumptions that make things simple enough that the standard methods can apply. Renner and Schmetters showed that they could solve general principal agent problems. The key thing was that you had to have the key components had to be polynomial functions. And by the way, that's not really a serious restriction. When you think that pretty much any utility function that we use in economics can be well approximated by polynomials. And they're extending that in a second paper now. So these are new algorithms that are available now for solving a wide class of economics problems. And to fully exploit them, one really needs to go to high power computing. Now, the other part of the future is not just getting stuff we know how to do and putting it on powerful hardware. The other part of what we should do is look at the algorithms and the software that's available to us from the computational science literature and use ones. By the way, there's of course an enormous amount there. Most of it is useless for economists. For example, economists have no need for, let's say, the equations that describe jet planes flying through the atmosphere. We don't have those kinds of problems. But there is a lot, if you look carefully, you'll find a lot of software in the computational science literature that has obvious direct usefulness in economics. Now, one example of this is derivative-free optimization. Now, derivative-free optimization is when you're trying to maximize a function, but without making assumptions on that the objective is highly differentiable. Now, in my course, you saw that the Nelder-Mead method algorithm was such a method, derivative-free optimization. However, that's a very crude kind of method. And typically in economics, the objective functions may not be smooth, but they are like smooth functions with some noisy ruffles on them. So these are called noisy objective functions. By the way, that comes out of maximum likelihood or moment criteria problems. If you're doing simulated maximum likelihood or simulated moments, you're going to have these kinds of objective functions where the Monte Carlo simulation noise is going to generate some wiggles around the true function that you're trying to minimize. Now, there's been substantial progress in that in the last 10 years or so, and in particular by Stefan Wild, who is from Switzerland, but is now at Argonne Labs outside of Chicago, and then his collaborators. And the idea behind a lot of this software is that the objective function may be non-smooth. However, it looks like it's a smooth function plus some noise. So basically, the idea of these algorithms is to smooth out, separate the noise from the underlying true smooth function, and then use that insight to optimize it. And the software that he has is called Pounders. Now, back in 2013, when Philip was a postdoc at Chicago, and I was teaching my course at Chicago, and Philip was a student, I think every day he was, every lecture he was there. And so in conversation, we were talking about some econometric problem he was doing, trying to solve some, I don't know, likelihood problem or whatever. And I said he should contact Stefan Wild, because I thought that his problem was the kind of problem that Pounders could do well on. And then Eisenhower, in a paper with Heckman, did use Pounders. By the way, I'm sure Heckman didn't have anything to do with computing anything up, so I say Philip did it. And the comments in the paper say that Pounders was very helpful in dealing with the optimization issues. Now, I also talked with Stefan Wild, and he said that Eisenhower's problem was not very challenging for Pounders. So there's a lot of problems in econometrics, which involves trying to optimize a non-smooth function, particularly if it's a simulated maximum likelihood or simulated moments method. Those are not going to be smooth, or even if they're smooth, maybe in some sense. Maybe they're actually C infinity, however, they're wiggly. They've got noise in them. So it strikes me as a tool that could be very useful in econometrics, and Philip's paper argues that it was. Now, so I told Philip about this 7 years ago. I gave him a 7-year head start, but now I'm starting to advertise it. Now, this morning, I got an email from Philip updating me on the progress, telling me that Pounders is now incorporated into a software toolbox that he is building at Bonn, which I'm very happy to hear about. So there is progress on this, and he's pushing it forward, and that is great, because I think this is a kind of computational tool that could have big impact in econometrics. Also, by the way, it is, I do know that there are versions of it that are parallelizable. I don't know exactly if the problems that Philip are looking at can use the parallelization. However, hopefully, perhaps after a reformulation, parallelism will be exploitable. But anyway, so that's an example of one kind of software which was sitting out there at Argonne and waiting for somebody in economics to use it. Philip is using it and promoting it, and that's great. Now, and by the way, this, like I said, this derivative-free optimization is a kind of stuff, had we gone into a second semester, this would be one of the things I would teach. So the basic ideas behind it are stuff that you can understand and comprehend. So this is exactly what you would have seen if we had gone on for a second semester. Now, another topic which I had wanted to include in the course, but you can't overload it.
I never wanted you to stop. Yeah, if you want a second semester, I'm sure we find you a crowd just in case you're fishing. Yeah, so
now. Okay,
you have better things to do. I know.
Yes. Okay, so I'll make sure I address that second semester issue before we end. Now, another topic that I'm very interested in is the solving polynomial equations. Now, by the way, in much of economics, for example, in particular in I/O theory, generally demand curves are linear, supply curves are linear. Occasionally, maybe they're piecewise linear, but that's about it. Now, so what basically we know in some cases that changing, for example, if you change demand curves from being linear to being constant elasticity, you're going to get dramatically different economic results when it comes to talking about markups, for example. So wouldn't it be nice to go beyond linear specifications to, let's say, polynomial specifications? And not rely so much on linearity. Well, that's where computational algebra comes in. Now, Felix and Carl got me interested in part of this, sort of the very mathy theory part called Grosvenor bases. And Grosvenor bases, you take a system of polynomials, and I will argue you essentially, after you transform it into something that I say is essentially closed form solution to systems of polynomials. Essentially is because the computational burden is very low once you've done the transformation. So now what TJ Cannon and I are doing is working to deploy versions of these Grosvenor basis methods that can exploit massive parallelism and take that to supercomputers. And by the way, TJ Cannon happens to be at University of Texas, the same location as Stampede, the supercomputer I mentioned earlier. And so this will allow us to solve, I think, very interesting 2- and 3-stage games in I/O that are right now are solved, but using extremely special assumptions. I'm sure there's other kinds of applications also. Now, a mathematician at Notre Dame called Andrew Samezi, a long time ago, I met him, and he introduced me to Bertini, which is software which will compute all the solutions numerically to a system of polynomial equations. And it also is parallelizable. So the Grosvenor basis stuff is purely algebraic, very theoretical. The Samezi stuff is basically numerical, and there's 2 ways here of solving systems of polynomials, very different in their basic background mathematics, but both of them are capable of solving large systems, and both of them could be very useful in economics. Now, you heard me talk about multi-objective optimization. That was a lecture a couple of weeks ago. And this idea has been around a long time. Philip and I are just scratching the surface of it now to solve optimal tax problems that are literally intractable by any standard approach. Now, on the software side, Philip and I are writing our own software because we know special structure about the functions that are involved in this multi-objective optimal tax problem. In fact, that they're all smooth and differentiable and nice. Now, in engineering, a lot of times the problems are partially integer, maybe discontinuous objectives. And so Pat Reed, who is now at Cornell, has written a very much of a general purpose multi-objective optimization software called Borg. This, of course, is an obvious reference to the Star Trek TV series and movies. Now, so you have a general purpose tool there. We're going to come up with something that's much more efficient for a limited set of problems, but multi-objective optimization is another part of computational science which should be used much more so in economics. Now, in approximation methods, what I did is I basically taught you the classics, the polynomials, approximation methods. I did introduce you a bit to neural nets, but not a whole lot. That was just basically a teaser, a little appetizer I gave you. But there's a lot of approximation methods now that are becoming available, that are being developed. Sparse grids, I referred to Simon Scheidegger's work, Gaussian processes. That's also something that Simon has written a paper on. Neural nets. Actually, some of Felix's students, Luca and Simon, and I think there's a third one involved, that are using neural nets to solve overlapping generations models. And then there's a topic of machine learning, which is becoming popular in some circles. I don't see how it'd be useful for solving the kinds of equations we've been looking at, but who knows? Maybe it could be. So this is all stuff that's out there available for economists to use, and some are starting to use it, and that's great. Now, the other thing that we have to keep in mind is that if economics is going to progress and take advantage of what's available, it has to build connections with the math people who have the software, who knows the computational science. And now I will give you here a list of my connections. And so this is very much of a personal list. Others may have other connections, but this is what you have. If we're going to progress, we have to build connections and collaborations with people like this. Now you've heard me talk about Todd Munson, and he was the author of Path, which is the best CGE solver around. Stefan Wild, Pounders, Pat Reed, I mentioned about Borg. Now, Michael Saunders, I mentioned, helped me with optimal tax paper. Sorry. And then, okay, let me get. There. Yeah. Okay. So, yeah. Now, Michael Saunders was very helpful in that tax paper. He's been helpful on a variety of times with working with me and my students. Andrew Samezi, I mentioned. Now, I've written papers with Stephen Wright and Greg Thane on the use of Condor. I've written papers with Doug Thane, who's a computer scientist at Notre Dame, on developing what Doug Thane likes to do is think about writing software that is designed for specific problems with a specific form. And so I told him about how a lot of problems in economics have a particular structure in terms of you solve these problems and then that and that. And then out of that conversation came what we called wavefront. And so it's a way, it's a kind of structure to a problem which allows it to be parallelized. And so then this concept wavefront was then used to build some software for parallelizing such problems that is designed, that takes advantage of that structure. See, Doug's theme in his work is that computer scientists need to get closer to the user. Computer scientists say, okay, I've written MPI and OpenMP and all that. Now you guys, you're on your own to use it. And now, of course, the problem is, no, it's hard to learn all that stuff. So Doug said what we should do is identify particular kinds of problems with a particular structure in terms of the dependency of problems, and allows us to schedule parallelism, and then write software for those particular kinds of problems. We can make it more user-friendly. And that's what Doug and his students and I did in a couple papers. Carl and I are working with Michael Ferris, who was Todd Munson's advisor, on using Path for dynamic games. Now, also, I don't know, somebody at Zurich, my suspicion is that Gregor Reich was involved, but I do know also Philip has been involved. that some Zurich people made connections with the guy behind ADIMAT and the guy behind Casati. And I remember going to Zurich and meeting the mathematician behind ADIMAT. And he gave a presentation on ADIMAT and its development. And I do know Gregor and Philip are in contact with the Casati guy. But they illustrate a problem in that ADIMAT was kind of a hobby for the mathematician. Basically, I think what it was that when a graduate student came along, he'd say, okay, I want to extend ADIMAT but this way or that. And the graduate student would do that, get a PhD. But there was no focus on creating a finished product. However, more recently, that's made substantial. So I knew about ADIMAT, 10, 15 years ago, but I also knew I really wouldn't want to recommend it. But now it's much better because he's had more graduate students. And so a lot of times this mathematical software that's available is not designed to be commercial quality. So yes, it's free, but there's reasons why it's free. Now, Casati is a completely different project, and it also has the same kind of development process behind it. But by making connections with these people, we can understand that we can find out what the strengths and weaknesses are of this kind of software. And Casati has turned out to be very valuable. Now, as I told you before, I spent a week at Bonn, guest of Michael Griebel. He's Mr. Sparse Grids in the world of sparse grids, and he's at Bonn. And also what Philip Eisenhower told me today is that he is working with Michael Griebel on some joint projects. So Bonn appears, now so it's great to see at Bonn something that's happening that should be happening in many more places. I do know Michael Griebel, and he is very interested in having economists use this. He's very supportive of economists using this stuff, as far as his stuff. I was a plenary speaker at a conference that he was main organizer for. So he's very supportive of that. And now with Eisenhower, I'm glad over the years has now built bridges with Michael. And so that's what's needed in more places. I've done that with Michael Saunders and some OR types here. And that's going on at Bonn. That's great. That's what's needed, because there are many gold mines of software out there that can be directly applied to economics. We need to work to get that happening. Now, the other feature about where we have to do better is training. And now this course was an example of the kinds of things that I have been doing over the past years. Now, what do other fields do? This is, what do other people do? Now, by the way, back when I was a college student, the computer science departments taught all the numerical analysis courses. That isn't the case anymore. What's happening is that basically different fields develop their field-specific courses. However, their courses, the material is based on sound numerical analysis and is based on mathematics and not on some flying by the seat of your pants kind of stuff. And also they have many workshops training people, and the training is multidisciplinary. So you may have various different kinds of engineers at a workshop learning the same kind of software, but that makes it useful for everybody to see how software and algorithms are used in different contexts. We need to follow that example. Now, as I indicated, economists and computational scientists don't interact like they used to. There are reasons. Computational scientists think economists don't know much math. Economists think computational scientists don't know much economics. And after having dealt with both, I will say that both are right. Now, computational, see, one reason about computational scientists not understanding much economics is they're used to let's say, engineering and physics kinds of problems. And the thing about physics problems in chemistry is that ultimately you're dealing with the motion and properties of particles. What you have to remember is that people are not particles. See, if you pick up a ball and throw it at a wall, the ball is going to continue to go towards that wall until it hits the wall and breaks or it smashes, whatever. However, if you pick up a person and try to throw him to the wall, he's going to resist because he has some foresight as to what's going to happen. And that's the thing that's present in economics that's not present in physics. Too many, I remember even when I was a math grad student, listening to mathematicians talk about public policy, they would say things like, well, you just pass a law. And no, you can't just pass laws. You have to enforce them, and you have to have people that are supposed to basically have to support the law if they're going to obey it. In order to eliminate alcoholism in the United States, we made alcohol illegal in, I don't know, roughly 1920. Well, that didn't work out so well. So we had to stop that exercise. You have to think about economics. You have to think about the fact that you're dealing not with particles, but with people who have expectations, foresight, and are not just particles. And so this is a problem in dealing with, in bringing computational people into economics. You have to make sure that they know that we want them for their math skills. We'll entertain some comments on the economics, but then what you have to do sometimes is go and give them a little short mini course on the economics. I know I had to do that with the optimal tax stuff when talking with Dingma and Michael Saunders. They would look at this optimal tax model and said, well, you've left out this, you've left out that, blah, 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 blah. And I said, yes, yes, yes. But basically then pointing out to them that anything that had all those real world features that they wanted in the model would be completely impossible to solve. So anyway, this is when you're talking with computational scientists, you have to tell them a little economics in order for them to understand where we're going. Now, collaboration is really necessary for serious progress. And by collaboration, I don't mean what you see in economics. In economics, a lot of papers come out of, a bunch of guys go to a bar and drink, and then they talk about a paper, and then they end up writing a paper together. That the people on a paper is really a club of clones. They all have roughly the same expertise in the same areas. In science and engineering, you look at any of those projects involved in anything, what you have is people with different skills and expertise working together. That most of the people have no idea what most of the other people are doing, but that's how you get planes built. That's how you get rockets built. That's how serious things are done. Now, this is not done in economics, and now maybe that's okay for academics, but when it comes to economic institutions with policy responsibilities, we should encourage the approach of science and engineering, of collaboration and bringing people with different skills together. Now, that's not easy. That's not trivial because economists and computational people speak different languages. I suspect that's true of different kinds of physics and engineering. And so when planning a conference once, Lars Hansen said, well, we need to have a translator, somebody who can at least speak to both groups, maybe not be an expert in either one, but can speak and translate. That's what's needed and needs to be encouraged. Now, there's an example in terms of collaboration. I like to point to of this kind of the science and engineering kind. Point to the climate paper I talked about on Tuesday. Now, Young Yang and I've been doing computation for a long time. Young Yang was a computational science a PhD student, but neither one of us knew much about the climate literature, what was interesting or what was not. But then Thomas Lonchek was very well acquainted with the climate literature and what the themes were of what people are interested in. And so we added on we included in the tipping. Thomas was particularly familiar with the tipping point literature in climate. And so he helped us include that in a sensible way in our paper, and did the calibration necessary to make that module reasonable. And also then he introduced us to Tim Lenton, who is a guy who works only on climate stuff and is one of the leading people working on tipping points. So that's how you should build collaborations, not just talk to clones of yourself, but reach out and talk with people with other expertise, bring them into the project, and then you start to create a network. That's not done much in economics, but it should be done much more. Now, recruiting. Now, the problem is in economics is that if you have serious quantitative skills, what's going to attract you into economics? Now, if you're a physics major, chemistry major, computer science major, and you're an undergraduate, you may think about taking an economics course. But afterwards, you're going to say, well, that was interesting, but no way am I at all interested in going into economics. I remember I had the same reaction back when I was, I think, a sophomore in college. I took intermediate microeconomics. And I remember the professor, Claudia Golden, who went on to be a leading economic historian, but I had her for intermediate micro. And one day after she went through this graph of income and substitution effects using the graphical method, and I thought, this is awful. You should just write things down with calculus and you get to the answers very quickly. And afterwards I said to her, well, this would be a lot easier if you just use calculus. And she said, I know that, you know that, but that's just not allowed in undergraduate economics courses. Now, that was in the early 1970s. Now, my impression is that this still is the case for most of undergraduate courses. Now, by the way, that was the last economics course I took for many years, because if I can't use calculus, what's the point of studying economics? But then I became aware later that economics can be very quantitative. But many people who would be interested in going into economics research with quantitative skills, they're not going to see anything as undergraduates to attract them. Now, there is an example, a counterexample I like to point out. This was, I forget exactly the year, roughly 2010, something like that. I was asked to give a talk to undergraduates at BYU now these are undergraduates. These are not high power math types or science types, but they're sort of a regular BYU undergraduates. And I talked about, they wanted me to talk about my economic research, and I'm at a level approachable to them. So there's this one guy who was a chemistry major, and he was at a course. That course ended, and then he was just kind of tired. He just didn't feel, basically inertia made him sit there, and then he kind of heard that this guy, Ken Judd, is going to come in and talk about economics. And so he decided, well, I'm going to listen to this. So he was a chemistry major. I presented some quantitative stuff, but at an understandable level. And after that, he decided to go to graduate school in economics. So now, so I was pleased. I was actually kind of shocked that me talking for about like an hour or so. The guy changed his major. I mean, he must not have been devoted to chemistry, but anyway, I think it's just an example of how if the information gets out, we can attract quantitatively skilled people to economics. Now, the other source of talent for economics research is postdocs. From basically anybody who gets a PhD in physics knows that the life expectancy of their physics career is short. And so some decide to get out soon. Because physics PhDs, the best ones, they'll get offers of being a postdoc at somebody else's lab, but then they're postdocs in physics and science in general means you're kind of somebody's slave. And so then maybe stretch that out for a while, but basically the chances of you becoming a professor is really quite slim. There's lots of money to hire postdocs. There's not lots of money to hire professors. So many times these PhDs in physics will leave the physics world voluntarily or involuntarily. Now, many of them have gone on into doing computational finance. Been sort of a steady flow. But that doesn't help us at all because we need them doing economics research. Now, by the way, it's not the case that all physics PhDs are going to be great in economics. Physics PhDs may have high IQ, but the problem is you also want to have somebody who has some common sense and understands something about economics. And there was one project that I was involved in where we spent a lot of money on a PhD, physics PhD, and it didn't work out so well. Now, let me tell you about a story that did work out well. So many years ago, Carl and Felix tells me that there's this guy who has a computational astrophysics PhD that wants to come to Zurich and study economics. And they asked my opinion of that. And of course, I was skeptical, but I said, send me his vita and a copy of his PhD thesis. So I looked at the PhD thesis, not that I could understand any of the physics, but I looked at what math was used. And I noticed that he was solving partial differential equations, and some of them were of a type similar to economics. And he was familiar with solving partial differential equations, and I figured, well, the methods he's using look like they could be transferred to economics. And so then I went to Zurich on regular business. And so then Carl, Felix, and I had lunch with this guy, and I told him what I thought, that yes, his skills were ideal, could be applied to economics. And I mentioned to him that I knew Bob Rosner, and he was a Bob Rosner groupie. That doesn't mean anything for most of you, but you should have seen the look on his face when I told him that. And then I also invited him to come to ICE in a couple months after that, which he did. And so now then, of course, somebody needed to have money. Well, I didn't have money. Carl didn't have money. Well, Felix had money. So he went to work for Felix as a postdoc. And I'm talking about Simon Scheidegger. So who then his expertise, sparse grids, et cetera, is now in economics. So there are people out there who would love to be doing economics and love to use their skills in economics. We have to go looking for them. We have to employ a careful filter, but they are out there. And we need ways to do this that are not just so random as in the case of Simon and Carl talking with Felix, Carl, and I. So that's what we need to recruit people with those talents and bring them into economics. So now that was a list of things to do. And if this strategy is followed even partly, then I think as far as computation in economics is concerned, we could have an explosion. Thank you.